Hello everyone, so you are welcome to this lecture. We are continuing with the matrix exponential. So in this lecture we want to finish off with computing how you compute the matrix exponential using the Putzer algorithm. Alright, so I'm going to state the theorem and I'll do two examples to illustrate how you apply it. Okay. So here's a theorem. It says that given the eigenvalues lambda 1 to lambda n, okay, they could be repeated, not necessarily distinct eigenvalues of A, then the matrix exponential is given by this expression here. All right, basically a sum of the product of these p's and m's, and then you have a way of computing what the p's and what the m's are. So m naught is equal to the identity matrix. Mk is given by the product of A minus lambda ii for k from 1 to n. In actual fact, k ends at n minus 1. Okay, I have a note that tells you that mn is equal to 0 actually when k is n from the Hamilton theorem. So you get the m's from this product, and the p's, you get these p's from solving an initial value problem. So P is a vector, P1 to Pn, and your IVP is given by this. P prime is equal to this matrix, where you set the eigenvalues to be on the diagonal, and below the diagonal you have 1s, and then 0 everywhere. So for example, for a 2 by 2 matrix, you're just going to have lambda 1 0 and then 1 lambda 2. For a 3 by 3 matrix, you just have this matrix here, right? And so on. And then these are the initial conditions for the resulting initial value problems. Okay, P at 0, when T is 0 is given by 1, the rest are zeros. So this is the remark I was talking about. By the Hamilton theorem, Mn is equal to 0. All right. So I've left out a proof, and I just want to illustrate with some examples. So here's a simple example. You have a 2 by 2 matrix, A is equal to 1, negative 1, 1, 3. You want to compute a matrix exponential. So basically you go straight away to solve for the eigenvalues as we often do. So the eigenvalues in this case, solve this. You get lambda 1 and lambda 2 is equal to 2, repeated. All right? So lambda 1 and lambda 2 are the same thing. So, so in this case, your matrix exponential is just equal to the sum from k equals 1 to k equals 0 to 1, right? This is n minus 1. We have two eigenvalues, so it ends at 1. And then you multiply p and m. If you expand this, you get p1 times m naught plus p2 times m1. And so basically all you need to do is compute what your P1 and P2 are, what your M0 and M1 are, plug them into this, the right hand side, and then you get a matrix exponential. That's all. So it's a kind of straightforward approach to computing the matrix exponential. So M0 is just the identity matrix, M1 is equal to A minus 2i, okay, if you go back to the product term, and that gives you this matrix. Now, if you let our P, okay, the vector PV, P1, and P2, we solve this initial value problem. P prime is equal to this matrix, where lambda 1 and lambda 2 are on the diagonal. In this case, they are the same. Just below the diagonal, you have 1 and then 0. Everywhere else, multiplied by P. P at 0 equals 1, 0. That's the initial condition. And so this equation will give us two initial value problems, right? So P1 prime will be equal to, multiply 2 by this and 0 by this. So you have 2P1 and you have P1 plus 2P2. So that gives you these two equations, initial value problems, which you have to solve sequentially. So solve this one first, that gives you P1, then you plug P1 to this and solve for P2. Easy. So solving the first equation, you get P1 is equal to e to the 2t times C1. From the initial condition, P1 at 0 is 1, which implies C1 is 1, and that gives you P1, which is equal to e to the 2t. So you get P1. So once you have P1, plug it into the second equation here, and you have an equation in only P2. right? That gives you this equation here. P2 prime is equals to e to the 2t plus 2p2, which you can rearrange. And this you see to be a linear first order equation, right? And we know how to solve that from Math450, right? So from here, compute the integrating factor, which is this. Multiply this equation by the integrating factor, and then you end up with this equation, and then the left hand side can be written as ddt of e to the minus 2t times p2 equals 1. Integrate both sides, that gives you this, and then p2 is equal to this. You can apply the initial condition that p2 at 0 is 0 and c2 is 0, and that gives you p2. So you have p1 and you have p2. So once you have p1 and p2, you plug them and that gives you your p's. So now we know the p's, we know the m's. You go back and plug them into, let's go back and put them into equation star. We know p1, we know m0, we know p2, we know m1. So you put them in there. When you plug them in, you get the matrix exponential to be equal to this. Rearrange terms, and boom, you have this equation: e to the 2t into 1 minus t, t 1 plus t. Okay. Now we have solved this same problem, okay, for the matrix exponential using the first two approaches, the previous approaches. So you can compare the two and see which one you prefer, which one you think is easiest to apply or to use. Now if you are asked to find a solution to a system x prime equals ax, then the solution becomes easy, right? Just take the matrix exponential and multiply by a constant vector c, and then that gives you the solution to the system.